This is a small-scale mock-up of an AI processor. If you'll notice, we wound up with about 5.23 milliamps of bias current. You typically can't really get away from that. You have to have something in the part to bias it up. The only way to reduce that is to actually redesign the part for lower biasing currents. If you notice in this particular clip, 25 megahertz clock is off, so there's no dynamic power. We're actually driving CMOS logic inside the part when we turn things on to generate dynamic power for measurement. In this clip, we're turning the clock on. We're disengaging the CC-100 PowerPad circuitry inside the part. You'll notice that the current jumped up to 8.37 milliamps. Subtract that from the static that we measured before. We wind up with 3.14 milliamps of dynamic current in the part itself from the logic. This is with the CC-100 PowerPad circuitry engaged. 7.95 milliamps minus the static gives you 2.72 milliamps. And this is the effect that the PowerPad CC100 circuitry has on dynamic logic on any processor or any mixed signal part. The math on this is pretty simple. Disengaged current minus the engaged current gives you 0.42 milliamps. This 0.42 or half a milliamp divided by 3.14 milliamps full scale current gives you a 13.3% reduction. And this is typical in any mixed signal or processor based part. It even scales into the amp region where you're actually burning amps of current and reducing current by amps. Same basic reduction. And this is why we are actually measuring the power grid on this board in particular and part. The green is essentially with us disengaged. The blue is with us engaged. You see a substantial reduction in spectral energy. And that's what we're harvesting and feeding back. Do a blink comparison on the two. You can really see it well. This denies hackers access into these parts via RF. My name is Michael Hopkins. My number here is area code 209-914-2305. We'd love to demonstrate this for you. We're actually the next generation in AI power reduction with this technology.